Hello, Assalamualaikum, and very good afternoon, everyone.
Good afternoon to you.
All right. Okay. So we'll proceed our class now. Okay. So I think some of students cannot come to today class, maybe because of the time clash. But I will just carry on the class, and they can see the recording. If they want to uh, and they have time after this lah. Okay, by the way, I'm very sorry to have class on this day. Okay, because I have problem on Friday due to the company to the visit to the factory. Okay, so I will share first the slides. Okay, do you see all the? Do you see this? Can you see the slides?
Yes, sir.
Okay, good. All right. Thank you, Paul. Okay, maybe I'll start now. The class. Okay. So last time we have finished until the. I think we will start with the SI units. Okay. Okay, for the SI units, actually this I think you all know about this. Okay, is very important measurement units for all. Okay, I think in the world they are using the SI units. Okay, in order to standardize the measurement units. Okay. Okay, first of all, the nature of the unit is the engineering quantities. Okay, which different kind of that are involved. For example, the physical. Okay, such as the weight, the distance, for example, and also the chemical. Okay, the molecule, the mechanical parts, the thermal, the electrical, and the physiological. Okay, this is all the quantities that need the units. Okay, and in order to record or to compare between each magnitude of the quantities, there is some one magnitude to each other need to be taken as a basis, as a standard for the units. Okay, each unit also must be represented by the physical standard of some kind, like a natural or artificial, which is must be derived from the combination of other units, okay, by representing by the standards. Okay, so the SI unit is can stand for System International Unites in French. Okay, which is this is from French words, which is the abbreviation is adopted by the International Standardizing Organization, which is ISO, and it can be used in many language lah. Okay, so I think all of you know about the ISO. Okay, even for ISO is very important standard. Okay, that can need to be need to be followed by each countries in order to to have a good standard on this on the any of the development of design of the products. Okay, and the SI unit is comprehensive, which is a logical and coherent system which designed for the science, engineering, and technology. And the SI unit system is consists of 28 units, where there is a 7 base units and also 2 additional units and 19 derived units. Okay, we know that in 28 units there is 7 base unit and 2 additional unit and also 19 derived unit. Okay, we can see what is the base unit. The base unit is listed like below. You can see the length, mass, time, temperature, intensity, current, and also the amount of the substance. Okay, where the I think you are from physics. When you learn at math in physics, for example, I think you start with 5. Okay, which is the LMT, time, temperature, and the electrical current I. Okay, and this the unit of this quantity, okay, is for length is meter, while mass is kilogram, time is second, Kelvin, candela for the intensity, and also for the current is ampere, and for the substance is mole. Okay, I think you are if you are studying on the chemistry, okay, we can learn about the mole. Okay? And about the abbreviation, you must know that for the meter is a small m, okay, and there is a kilogram. Okay, for the mass is a kilogram, not gram. Okay, and time is second. Okay, not hour, not minutes. Okay, and the temperature is Kelvin, not Celsius, not in Celsius. So that means after this, if you are finding any calculation for is including in the temperature, don't use Celsius. Please use Kelvin in the calculation. Okay. And for the intensity is candela is CD, and the current is A, big A, and for mole is mole, MOL. Okay, so this is the dimension. Okay, dimension is a representative of the symbols. Okay, we can see after this, which is the dimension is a derived unit, which is recognized by the dimension. Okay, and can be defined as a complete algebraic formula for the derived unit. Okay, this is a complete algebraic formula, which is in the dimension equation. Okay, the dimension equation is the conversion from the system of unit to another one. Okay, and it can also help to derivation of equation for the physical quantities and also checking the accuracy of the equation. All right. Okay, then for the convenience, some derived unit has been given new names. For example, for force, okay, since force is a combination of kilogram, meter, and also for the time, okay, uh, and we can call the force as a Newton, okay, Newton as the new name for the dimensional correct for the kilogram meter per second. Okay, and here is the example, okay, how we can do derivation units for the dimension, which is for example for the velocity is a derivation of the dimension from the length over the time. Okay, and we can get a v, okay, which is meter per second. Okay, this is called a velocity, and this will be a as you can see the derived units. Okay, there is a 7 base unit and also a derived unit, which is like v, come from the length and also time, and we can get a velocity. On the other hand, for the acceleration is the velocity over time. Okay, we can get a, okay, small a. For example, F equal to ma. Okay, for the force, which is mass, is a basic unit. Okay, and also the acceleration is derived unit. Then we can times it, and we can get the force. Okay, also with the work, which is work times to length. All right, and also we can get a joule. Okay, and also for the power, okay, which is power work over time, and then we can get a power. Okay, this is a dimension derivation of units. Okay, from this dimension, okay, actually we can get the dimension of the derived units. For example, for the v, we can get lt minus 1. Okay, and we can change the dimension into the directly to the what we call it as the units. For example, the unit abbreviation is m. For example, m s minus 1 for the velocity. Okay, so we can directly change it. For the length is m, t is s. So we can get the unit for the velocity is ms minus 1. Okay, and for the acceleration, okay, we can get lt minus 2. Then we can change directly, and also with the force, okay, mlt minus 2. Then we can get kilogram meter second minus squared. Okay, and also for the work also. Okay, so we can first you need to derive, okay, the dimension. Okay, and then we can change the symbols inside it, and we can get the units, derived units. All right. Okay, this is what for the example. Okay, for the velocity, acceleration, and others. Okay, so as the standard measurement, the measurement is a process of comparison. Okay, which is regardless of any measurement method, such as the basic of comparison must be employed, which is by using the standardized unit, and the standard must be precise, defined. Okay, which is with the different system of unit exists, the conversion method also mutually agreed. Okay, and the standard of measurement can be defined as a physical representation of units measurement. Okay, where the measurement is relied by reference to either an artifact or prototype, or natural phenomena, or standardized procedure using standardized measurement method and equipment. Okay, this is a standard of measurement, where the example is a unit of mass. For example, can be defined as a cubic decimeter of water at its temperature. For example, maximum density, and represented by a metal standard, where the standard is known as an accurate measure of physical units. Okay, this is we can call as a standard of measurement. And also, we can define the standard of measurement into four categories. Okay, which is the categories for the standard can be up to international standard, and then the primary standard, secondary standard, and also the working standard. Okay, based on these standards, okay, there are some categories. For example, in the international standards, it will be defined by the international agreement, which is they represent certain units of measurement to the closest possible accuracy. Okay, that this standard also periodically evaluated and checked by the absolute measurement in terms of fundamental units. Okay, for the international standards, they are maintained. These standards are maintained by the International Bureau of Weight and Measures in Paris. Okay, so that means in overall in this world there is only one. Okay, the benchmark. Okay, to maintain the standards. Okay, for example, for the weight, they will be in Paris. And also these standards are not available to ordinary user. for purpose of day-to-day comparison and calibration. Okay, that means for ordinary people or ordinary apa nama even country cannot compare it and calibration it based day-to-day punya calibration. Okay, it needs to be contact to the International Bureau of Weight or Measurement in Paris, for example, in order to calibrate it. All right. So for this is the international standard. This is very accurate measurement. On the other hand, there is a primary standard, which is the primary standard has the main function of primary standard, which is it can be verified and calibrate the secondary standard. Okay, so the secondary standard will will refer to the primary standard to make sure that the level is accurate. Okay, and for the primary standard, you will see the international standard to make sure that the primary standard is no error or accurate. All right. So these are calibrated independent by absolute measurement of at each of national laboratories. Okay. So that means at national laboratories, for example, in SIRIM, okay, which is or the Department of Standards, okay, they have the national laboratory that has the absolute measurement that periodically has been calibrated with the international standard. Okay, then the result of such measurement are compared and against each other and leading to the world average figure for the primary standard. Okay, however, for the primary standard are not available for use outside the national laboratory. Okay, for example, in factory, for example, if you want to have the calibration, okay, you need to submit to the national laboratories to make sure that our measurement device are good to use and highly calibrated. Okay, and for example, in Malaysia, this function is carried out by SIRIM. Okay, and for the secondary standard is a basic reference standard, okay, which is used by measurement and calibration laboratories in the industry. Okay, so that means in the industry there is a laboratory, okay, to make sure that the device is calibrated. Okay, and each laboratory periodically send its secondary standard to the primary standard. Okay, in national standard laboratories. Okay, sometimes, okay, for example, our weight measure. Okay, so because of we have used it every time or daily. Okay, we need some of the calibration may be loose and then need to be sent to the primary standards laboratory to make sure that it's calibrated again and to make sure that align again with the primary standard. Okay, and then after the calibrated, the secondary standard are returned to the industrial laboratory with the certification of measuring accuracy in terms of primary standard. Okay, so that means after calibrated in the primary standard, they will put a sticker, for example, a sticker that has been calibrated from when to when, okay, and need to calibrate it again, expired after some time, and need to, if you want to say that the device is good to use, is the device that always been calibrated, okay. And on the other hand, lastly, the working standards. This is the principal tools of the measurement laboratories. Okay, they are used to check and calibrate the instrument used in the laboratory. Okay, because for example in the factory, okay, there are a lot of laboratory. Okay, and there will be one. Okay, for example, the benchmark, the reference of the standard, the secondary standard, and all the others laboratory will refer to that. What we call it, the device, okay, to make comparison measurement in industrial application. Okay, for example, the manufacturer of the electronic component, for example, such as a capacitor, resistance, and many more, use the standard of the working standard to check the components value being manufactured. Okay, to make sure that the for example the company manufacture the LED. Okay, then the LED need to be, or the resistor need to be checked before it can be manufactured. Okay, that is and it is widely used for the calibrating laboratory instrument for carrying out comparison measurement for checking industrial products. Okay, uh, if you want to make sure that the product is in highly accurate performance, okay, the industry need to periodically send their products, their working standard device to the secondary level to check either it's already good or not. Okay, so if you see the category here, from the definition to the where we can find it. Okay, for example, for the international standard, we can get from the World International Agreement, and the ordinary user cannot use it. While for the primary, okay, we can go for the national laboratory. Also, the ordinary user cannot use it. Okay, only the specified person or the accredited lab can use it. Okay, and also for the secondary, okay, this is in industry, okay, where the industrial laboratory available for ordinary user to check and measure working standard. Okay, this is the reference for the working, and primary is the reference for the secondary, while for the international is the reference for the national institute. Okay, so if you see for the working standard in the industry or the laboratory, it can be used for the day-to-day basis. Okay, for example, the resistor, capacitor, etc. Okay, so you can see here about the accuracy. Okay, when we talk about the international standard, the accuracy is very, very high. Okay, while for the working standards is very low because it has a lot of level until the international standard. If we have, for example, between primary standard and to the international standard is around 0.001%, but when it come to down level, it become times to 100. For example, 0.05 or 0.5%, for example, the accuracy will be reduced. And these working standards are used as a measurement reference on a day-to-day basis, while the second standard is more accurate than working standard, which is throughout the industry for checking working standard, while for the primary standard is more accurate than the secondary standard, okay, where it maintain the highest possible accuracy by national institution, while for the international it maintained by international agreement and may be used for checking primary standards. Okay, so this is the summary for the standard. Okay, for the standard of electrical measurement, okay, there is a few SI electrical units. For example, we know that sekejap saya ada call je. Alright, sorry for the disturbing. Okay, and here in the electrical units, there is a current standard and also for the voltage. Okay, we know that for the Ohm's law, we have the current, voltage, and resistance. And I think you have learned about the electrical circuit too. Okay, that you can also find the inductance, okay, the coil, and also the capacitance standards. Okay. Uh, okay, in the standards, there is a current is the quantity of the electricity charge, which is the column, and then that pass a given point in the conductor. Okay, So the electrical charge, okay, when it go through the conductor, okay, pass through it every 1 second, then the change of the charge is I equal to Q over T. Okay, so that means at one point, if the charge is going through one point at a certain time, which is 1 second, we know that the current is the quantity of the charge over the T. Okay, if you if you know that there is a lot of a higher current, okay, for example 100 ampere, for example, that means there is a lot of charge, okay, a lot of charge that are passing through at one point, okay, at 1 second. Okay, for example, if okay, for example this one, okay, for example this one is 3 ampere. Okay, sorry. Okay, 3 ampere. Okay, that means at 1 second only 3 column of electrons are passing through at one point. Okay, so that means the more electrical charge, the higher ampere. Okay. Okay, you can see here one column is around 6.24 times 10 over 18 electrons. Okay, so if you want to have one ampere, so that means this is the amount of electrons. If 3 ampere is time 3, okay, if 100 ampere is means time 100, okay, so that means it's a lot of electrons. And then the voltage is the potential difference, okay, which is the potential difference between 2 points. Okay, if we have maybe later lah I show the slide, the circuit. Okay, so basically for the term of voltage is the potential difference between 2 points, which is it carry the 1 ampere when the power dissipated between this point is 1 watt. Okay, so you see, if the voltage is in the electromotive force, which is EMF, the potential difference is 1 watt equal to 1 joule per second. Okay, which is what is P over work over time. Okay, work over time, then we can get for volt is a watt over ampere. Okay, which is when we put joule over per second into the ampere, we can get the J over S, which is a power. Okay, where the J is Newton over M, where work over energy, then we can get the Newton is a kilogram meter per S squared. Okay, here 1 joule is considered as 6.24 times 10 over 18 electrons, which move to the potential difference is 1 volt, and the electron carries a charge is 1 over 6 10 over 18, okay, column, and we can call it for 1 electron move through 1 volt, it can call as a 1 electron volt, EV. Okay. And the EV is the very small energy level, which is associated with the electron in orbit around the nucleus of the atom. I think if you learn about the quantum, okay, quantum electric, okay, you can learn about the Schrodinger and also the electron that around the nucleus. Okay. And also we know that there is also a resistance standards, which is the resistance is the ohm, which is defined as the resistance which permit the current flow of 1 ampere, okay, when the potential difference of 1 volt is applied to the reference. Okay, when we come to 1 volt over 1 ampere, we can get the 1 ohm. Okay, for example, for this is the derivative units, okay, which is voltage over I the current, and we can get ohm. Okay, you cannot put the V over A. Okay, you can put it, but the better you put in ohm. Okay, because the resistance has ohm as its uh, units. Okay, and for the inductance, okay, I think when you study about the electrical circuit, or maybe I don't know which subject. Okay, so for the inductance, you are learn about the unit is the Henry. Okay, and the Henry is when an EMF of 1 volt is induced. Okay, means the inductance is used to induce it by the current changing at the rate 1 ampere per second. Okay, so that means 1 volt is induced at 1 ampere per second, then we can call it a Henry. Meanwhile, for the Weber is the magnetic flux, which is the Weber defined as a magnetic flux which linking a single turn coil, which is 1 volt when the flux is reduced to 0 at a constant rate at 1 second. Then we can get a magnetic flux which is in unit is Weber. Meanwhile, for the magnetic flux density, okay, for the magnetic density, we can call it as Tesla. Okay, this is how we can go for 1 Henry, we can get 1 Weber over 1A, while 1 Weber is 1 volt per 1S, and you can get the L. L for the inductance is a 4 pi squared times to this over L for the length. Okay, which is N is the number of wire turn. Okay, how many wire is turned on the inductance. Okay, while for the R is the solenoid radius. Okay, how big the solenoid. Okay, we can get the inductance. Okay, while L is length of the solenoid. Meanwhile, for the fifth units is a capacitance standard. The capacitance is in farad, okay, which is for the capacitor, and the farad is the capacitance of the capacitor that contains charge of 1 coulomb when the potential difference between its terminal is 1 volt. Okay, you can see 1 farad is 1 coulomb over 1 volt, and you can get the yi is equal to q over t, then we can get the q equal to it, and c coulomb is equal to q over t. Okay, we know that 1 q is 1 ampere times to 1 s, okay, in 1 second. All right, so now we go for the next chapter, okay, which is in the part 2 is about the performance characteristic. Okay, last time we have already learned about the electrical measurement, including the electrical units and also the physical units. Okay. Now we go for the next is about the performance characteristic. In performance characteristic is can be defined into two, which is a static and dynamic, which is inside it is also the error and also the noise. Okay, first we go for the performance characteristic, which is in this performance characteristic, it can be defined as the characteristic that show the performance of the instrument. Okay, for example, we can know the performance characteristic can be example the accuracy. Okay, how much the accuracy of the sensor, for example, the precision. Okay, what is the precision? How about the resolution and sensitivity? I think during the class for the mechatronic system, intro to mechatronic system, okay, you will learn about this. Okay, how to find, how to select the sensor, etc., based on the accuracy, precision, and resolution and sensitivity. Okay, on the other hand, there is also the importance of the performance characteristic, which is it allows the user to select the most suitable instrument. Okay, for a specific measuring job. For example, you need to select the best sensors to be used in your measurement. Okay, For example, you want to find, not sensor lah, the easiest one, for example, the best ruler, okay, or the tape, okay, to measure your the distance, for example. Okay, this is, you need to select which one is the good one, based on the accuracy, the precision, resolution, and also the sensitivity. Okay, and for the basic characteristic, there is two types, which is static and also dynamic. The static characteristic means measuring a constant process condition. Okay, constant means fixed lah. Okay, fixed quantity. While for dynamic is measuring a varying process condition. So that means it can be always be changed. Then we need to have the characteristic of the instrumentation through dynamics. Okay, which is when you use the dynamic one, it can measure the varying process condition. Okay, is always adapt to the change. And here you can say that for the static characteristic can be divided into several types, which is the sum of items that will be discussed are followed. For example, the accuracy. Okay, what is the accuracy? And the precision and resolution, sensitivity, expected value, and also error. Okay, this is the characteristic for the static. Okay, and for the accuracy, okay, is the degree of the exactness, which is the closeness of the measurement compared to the expected desired. Okay, later we will see what is the difference between the precision and also the accuracy. Okay, so from here you know that the accuracy is the degree of the exactness. Okay, if you are apa nama tu, arrow, okay, what is the what we call it, the measurement consider the high accuracy or low accuracy, or high precision or low precision. Okay, and this you can measure it based on the relative accuracy, where yn minus to xn, which is yn is the expected value, which is the center, for example, and xn is the measured value, is what the real measurement is currently measured, and we need to compare it, either the accuracy is high or low. Okay, for example, now the expected value, okay, the expected value is the reference, okay, the reference value minus to xn, which is the measured value, over yn. Okay, then we can get 1 minus this method, and we can get 100%. Okay, so now, for example, if we say that there is a error for the measured value, then it will be calculated and times to per 100. Okay, so we can get 8 times to 100. Okay, so for the precision, measure of the consistency. Okay, even not accurate, but it's precise. Okay, every time you measure, it's still okay. For example, the accuracy is, katakanlah, the point middle is 100, is 10. Okay, but you are not accurate, but you are precise, because why? When you for example, you shoot, okay, shoot, and then it go to 5, and always 5, so repeatability is high, then it goes to 5, and it show that it has a high precision while it has low accuracy. Okay, for example, you can see based on the value of the 9n measurement is xn. When we minus to the average set of measurement, we can get the can get a precision. Okay, for example, okay, you may see this. Okay, what is the this is the comparison between accuracy and versus to precision. Okay, maybe I can ask someone, okay, what is the condition of this part? Okay, maybe some of you, any one of you, how about this? I would like to ask Shukri. Maybe Shukri want to ask.
Uh, not accurate, not precise.
This is,
Uh,
how about the accuracy and high precision?
Low accuracy and low precision.
Okay, good. Okay, low accuracy, low precision. Okay, how about this? Any one of you?
Low accuracy, high precision.
Okay, Anwar. Anwar said low accuracy, high precision. Okay, good. Okay, and how about this? How about this?
High accuracy, low precision.
High accuracy, low precision. Maybe others, other than Shukri, maybe Fardin. Are you there? Or maybe Yap, Yap Jin Yang. Are you there?
Yes, sir.
Okay, how about this?
This one, um, accuracy, low precision. High accuracy, low precision.
High accuracy, low precision.
Precision.
Okay, good. Okay, thank you. And last one, who want to? Ashraf ada? Ning Ashraf.
High accuracy, high precision.
Okay, high accuracy, high precision. Okay, good. Thank you everyone. Anwar, Shukri, Yap, and Ashraf. Okay, all is correct. Okay, so this one is, if you are here is the targeted one. If you are near to the targeted one, is a high accuracy. For example, like this. And if your repeatability is high, for example, this and this is called a precision. So this means this is high accuracy, high precision, while this is high precision but low accuracy because uh, far from the targeted. Okay, all right. I think everyone knows about this. Okay, so if you see the sensors, for example, the sensor that you want to use in your project, okay, have high accuracy but low precision. Okay, then is it good or not? Hmm? The best is high accuracy and high precision, but maybe it's high cost. Okay, but sometimes you have a constraint on the cost, on the budget. Okay, sometimes you need to find the best performance of the sensors. Okay, so basically the better, like high precision, high accuracy. But if you can't find it, okay, you need to find like this. Okay, so but for this you need to compare with the others, better high accuracy, and you can make a correlation between the both sensors. For example, for me, when I'm doing the precision agriculture, okay, the precision agriculture, the sensors, okay, the sensors is uh, sometimes like this. We have a sensor that can precisely measure, but we don't know what is the targeted. So for me, for example, to measure the soil for the pH, for example, the pH normally for the pH sensor they give like this. For example, it give 8, 8, 8. But the real one is 7, for example. So we can calibrate it. We can calibrate it into the accuracy level, okay, by using the correlation between each. But if like this is difficult, okay, this is more difficult because it's very low accuracy and high, and you cannot average it, okay. All right, so next, the resolution. What is the resolution? The resolution is the smallest change or the interval in a measurement variable to which an instrument will respond. Okay, the smallest change. And also the sensitivity is a ratio of change in the output of instrument to change or of input or measured variable. While for the expected value is the design value or the most probable value that expect to obtain, okay, which is the targeted, for example. And for the error is the deviation of the true value from the desired value. Okay, so for example, this is the desired value, this is a real value, okay, the true value. Okay, what is the error between this and this? Okay, so you need to minus it, okay, from the true value to the desired value minus to the true value. Okay, so we can get the true value, desired value minus to the true value. Okay, desired means the desired the the absolute, okay, the absolute value. And in terms of error, there is some of type of error, which is the error can be come from the error in measurement, and also there is a type of error which is can be come from the gross error, or we can say that a human error, and also it can also come from the systematic error. For example, from the device itself, it has maybe it's not yet calibrated, okay, through the laboratory. Maybe it can go for the systematic error. And also the random error is unknown error. Random error is unknown error, where we don't know it come from the human or the device itself. Okay, for example, it come from maybe we can see later about how about the interference, for example. And the error in the measurement, it can be generalized in electronic components, or instrument is perfectly accurate. Okay, this means that we know that when it comes to the electronic component or the instrument, it's never accurate. Okay, it all have some error and inaccuracy. Okay, still have accuracy. Okay, inaccuracy. Okay, so it's very difficult to define the true value. Okay, there is always some difference, either small or large, between the measured value and the true value of the unknown quantity. Okay, so as the error may be expressed either as an absolute or percentage of the error. Okay, if you want to find the absolute error, you can just find as a expected value or the desired value minus to the true value or the measured value. Okay, I think you may confuse the words of the true value and the measured value. Actually, it's the same. Okay, the expected value is the desired value, like we use here, right? The desired value is the expected value. Okay, and for the percentage of the error, you can just minus over y over the expected value times 200. We can get the percentage of the error. Okay, as the relative accuracy, okay, when we come to the error, to find the relative accuracy, we just 1 minus to the relative to the error. Okay, to the error, which is we can find the accuracy is can be in percentage. If the percentage is the 100%, which is 1 times to the percentage of the error. Okay, like this. percentage of the error, and we can get the A times to 100, okay, to get the percentage of the accuracy. Meanwhile, for the precision, is the same with the accuracy. However, the xn is the value of the 9 measurement, the n measurement. So that means at the, for example, if we have a question like this, the precision of the 6th measurement. So that means the precision at the 6th measurement compared to the average. Okay, compared to the average has been calculated. Okay, so the precision is the value at the numbered measurement minus to the average over average, and you can get the precision. Okay, so here, for example, as an example, given the expected value, voltage value across the resistor is 80 volt. Okay, this is the expected voltage. Meanwhile, we are measured it as a 79. So there is a lack of 1 volt. Okay, because we are supposedly get 80 volt, but we measure 79 volt. Therefore, to find the absolute error is the expected minus to the measured. Okay, we can get E equal to 1 volt. Okay. On the other hand, the percentage of the error is equal to error over expect times to 100, and we can get is 1 over, because of the error is 1 volt, is 1 over 80 times to 100, and you can get 1.25%. Okay, and for the relative accuracy, it depends on this value, which is 1 minus to 80 minus measured, which is 79, bahagi dengan 79, and we can get 0.9875. Okay, 75. And also lastly, for the percent of the accuracy is just times to 100. Okay, 0.9875 to times to 100, and you can get the percent of the accuracy. If you see the percent of the error is 1.25 plus with the 98.75, you can get 100%. Actually, basically it's a 100 minus 2% of error, and you can get the percent of accuracy. Okay. This is the example for the error in measurement. Okay, this is very simple lah. Okay, and for the example 1.3, you are given the table 1, which is we have the calculated 10 measured value. Okay. Okay, from this 10 measured value, the first value you measured is 98. Second round is 101, third round 103, 102, fourth round 97, fifth 101, until 10 is 99. Okay, you know that you have like a arrow, the shooting mark. Okay, and at the center is 100, but you get around it. Sometimes you are get 98, 101, and others. Okay, as the precision, okay, if you want to find the precision, okay, P equal to 1 minus to xn, the desired, minus to the average. Xn bar is an average. So that means you need to find the average. Okay, because you will use the average at both upper and down. Okay, the average of the measurement value is a hasil tambah, is the I will call it the total of the xn. Okay, which is 98 plus 11, 101, 102, 97, etc. until 99 over 10. How many set? Okay, if we have in the table 1 is 10 set of number, then we can find 100.5 as the average. Okay, if the question is want to find the sixth measurement, okay, the precision of the sixth measurement, then the sixth measurement is 100, then we need to find 100 minus to 105 over 100.5. Then we can get, but we need to absolute it, okay, because we know that 102 minus 100.5 is 0 minus 0.5. Okay, since this is the absolute, so the minus will be gone. Okay, so 1 minus to 0.5 per 100.5, then we can get 0.995. This is how the precision on 6 measurement data. If we say that for example 8, okay, 8 is 98, okay, then we need to find 98 minus to 100.5 over 100.5, then we can get for example 2.5, okay, 2.5 per 100.5, and we can get another number. Okay, please beware about this. For the precision, if there is a question about this, please be aware about this. Okay, so here, okay, this is for the precision. Okay, so we already talked about the accuracy, and we already talked about the precision. Now about the error. Okay, the type of error is come from the three types of error, which is gross or human error, or the systematic from the device, and also the random or now unknown, nowhere. Okay. Okay, from this error, okay, we can know that the gross or error or human error can caused by the human mistakes by reading the instrument. Okay, may cause occur due to the incorrect adjustment of the instrument and the computational mistakes. Okay, sometimes we read it improper. Okay, and the problem is cannot be treated mathematically. Okay, it need to be treated by practice. Okay, and cannot eliminate, but it can be minimized. Okay, because sometimes like parallax. Okay, so it's one of the human error. Okay, sometimes when you measure in the laboratory, for example, there is some error, you can say like this is from the human error, or maybe from the parallax, or maybe from the device itself. Okay, there is some reasoning lah, okay, and how to show that your measurement is not accurate or what. Okay, so for example, improper use of the instrument, this error can be minimized by taking proper care in reading and recording measurement parameter. Okay, if you see about the reading, sometimes there's also a mistake on the recording. Okay, for example, you are in group in a laboratory. Okay, your friend said 9, for example, you are not focused and you put 7, then this is a recording error. Okay, and each from there it's will affect your measurement. Okay, so because of the recording error. Okay, that's for example the human error. If you are using the IoT, for example, okay, there will be a transparent, because it's what it's show in the sensors directly recording into the system. Okay, also into the cloud. Okay, and in general, the instrument change ambient condition to some extent when connected into a complete circuit. Okay, while the solution, therefore, several readings at 3 readings must be taken to minimize the efficient of the ambient condition change. Okay, so for example, in order to reduce the human error, we need to take a several reading. For example, 3 times, 10 times. Okay, in order to change to reduce the what you call it, the repeatability. Okay, and there is also type of error. For example, on the reading register value using multimeter. Okay, both multimeter must use proper scale. Okay, for example, if you are using the analog multimeter, is easily be mistakes. Okay, like a Rayleigh parallax when you are seeing from the left or right, not from the center. Okay. And for the systematic error, the technical error is due to the shortcoming of the instrument. For example, by the defective or worn parts, okay, for the aging device, or effect of the environment of the instrument. Okay, for example, you put it with uncontrolled area, okay, humid. Okay, that means kadang-kadang it's sometimes it's what we call it corrode inside the device. Okay, therefore it has a shortcomings on the instrument itself. And this error is classified as in statics and also dynamics, which is the static is caused by the limitation of the measurement device for the physical law governing its behavior, while the dynamics is caused by the instrument not responding very fast enough to follow the change in the measured value variable. Okay, so that means this is called as a technical error of the device itself. Okay, which the device itself is, for example, for the dynamic is a slow response. For example, okay, then it has a problem on the error. Okay, and also for the static, it has the limitation. Okay, on the measuring device. For example, you want to measure device on more than 10, but your tape is only 10. Okay, then is a static technical error. Okay, that means the limitation on the error is on the device itself. The type is come from the instrumental error. Okay, the mechanical structure itself. Okay, maybe the aging, and also the environmental error. Okay, from the humid, and also the observational error. Okay, from the uh, okay, and for the instrumental error inherent with the measured instrument, okay, because of their mechanical structure, okay, because of the improper calibration, or maybe no calibration is or the faulty instrument based on the friction of the bearing. Okay, for example, for the irregular spring tension, also the stretching also. And this instrumental error you can avoid it by using the apply the maintenance. Okay, so that means the sensor or the device itself need to be maintained, and also need to select the suitable instrument for the particular measurement application, and also can apply the correction factor. Okay, if you have the repeatability on that part, but seems the closest the targeted error, the targeted value is at same repeatability, same error, and we can apply the correction factor. For example, times to 1.3, trying to make a correlation on it, and also calibrated the instrument against standards. Okay, so we need to calibrate the instrument because of the aging or what. Okay. On the other hand, for the environmental error, is the external condition. Okay, for example, the humidity, the temperature, the barometer pressure. Okay, sometimes when we are in the normal land, we got such temperature, okay, accuracy. But when we go to upper level, it has, because of the pressure and the temperature is going down. Okay, then the value is change. Okay, this solution can be caused and can be avoided by using the air conditioner, for example, at that particular area, and also can seal the certain components in the instrument to make sure that it's protected. And also we can use a magnetic shield, okay, to protect it from the magnetic interference, and also new calibration under local condition. Okay, for example, like this, you can say that, for example, the compass. Okay, do you want use the compass? Okay, you need to shield the magnetic shield, or you need to calibrate it. Okay, for the observational error is like a parallax error. Okay, other than the systematic error, it also can be a parallax error as the human error. Okay, while reading the scale, the observer would tend to hold his head too far to the left or right. Okay, well, you need to read the scale to at the correct position. All right. Next is the random error, is the unknown cause. Okay, we don't know where it come. Okay, maybe the lightning, or maybe like the noise from outside, the electrical, from the atmosphere. Okay, occur when the all systematic error has accounted, when we already accounted all the systematic error, but it still come, but it still exists, and it but however it's only accumulated in small effect. It can be avoided by using the increase of number of reading. Okay, we can see the repeatability of the reading. Okay, and we can use the statistical method to obtain best approximation of true value. Okay, so as the performance characteristics, we can measure it in varying process condition, which is the instrument rarely respond instantaneously, and pure delay can use to encounter where the instrument wait for some reaction. Okay, pure delay means because of the slow response of the device, we know that it's already have a slow response, then we need to have a delay or wait a bit for some reaction to take place before we can get the value. Okay, for example, the one I used in my presentation last time. Okay, maybe I can show you. Okay, for example, like this, the gamma ray. Okay, for example, the gamma ray that I use to measure the potassium inside the soil. Okay, because of this, gamma ray is a passive radiation sensor. It needs time to absorb the radionuclide from the soil to be detected by the gamma ray. Okay, therefore we need time to measure it before it can give the value. Therefore, from this the spec that we know, the characteristic of the gamma ray, we need to reduce the speed of the tractor. Okay, we know that if we go tractor too far I have one friend from UK. They like this. Siapa? For example, here, my friend David. I can show you. This David has the problem to find. Okay, this is the real example. This David has the problem to to measure the gamma ray. Okay, it has the value of the GPS every time he go, but the data for the gamma ray is less mistakes. We call it dia tak dapat record lah. It's not recording, means zero data. This is how he asked me why it's why it's happen. Okay, because when they use for example here dia punya kelajuan I have been travel is 6 to 8 kilometer hour. Okay, kilometer hour. But for me, I use only 3 to 4. Okay, tractor speed. Therefore, this half from their speed. Okay, because from here we know that the calculation from our calculation, the needs to time to absorb the radionuclide from the sensor, from the what you call it, the apa panggil tu, from the soil. Okay, therefore if they are too fast, okay, so the way the the gamma ray cannot absorb, okay, cannot record the value of the potassium around it. Okay, that's why I recommend him to go for 3 to 4 kilometer per hour to make sure that everything absorb first, then they can go. So that means that we need to change the speed of the tractor, for example, okay, to make sure all that can be recorded. Okay, so there's a call as a pure delay. Okay, when we need to wait for some reaction to take place. On the other hand, we need to such a nearly always used to measure quantity that fluctuate with time. Okay, when it comes to fluctuate with time, we need to fit it. Okay, as the dynamic behavior of the instrument is determined by the subjecting force, its primary element, the sensing element to some unknown and predetermined variation in the measured quantity. There is three most common variation in the most measured quantity, which is the step change, the linear change, and the sinusoidal change. What is the step change, linear change, and the sinusoidal change? We can say that when it comes to dynamic, the step change is like a step. Okay, when it occurs, rapidly change. Okay, it occurs rapidly change from one level to one level, from 0 to 1, it rapidly, without any gradually. So here the linear change is change linearly, gradually with time. Then we call it is a linear change. Okay, but sometimes it's a no regular, okay, or irregular change. Okay, we call it a non-linear change. While for this, if we go for the time and the change is dynamic, we call it a sinusoidal, like a sine wave wave. Okay, and this is called as the magnitude of its change with a sinusoidal function of a constant amplitude. Okay, that means the amplitude is constant, but sometimes the amplitude is not apa kata, not fixed. Then we call it a non-linear. Okay, this is the characteristic for three type of change. Okay, maybe I give you for another one is more a non-linear change. Okay, for example, like this is sometimes it's hyperbolic or saturated or what. Okay. Okay, from this dynamic change, okay, the dynamic formula of characteristic instrument is based on the speed of response, the dynamic error, the lag, okay, and also the fidelity. Okay, the rapidity, which is the instrument response change with the measured quantity. Okay, and also for the dynamic error is term of the difference between the true and the measured value with no static error. Okay, and also for the lag is a delay on the response. Okay, okay, delay of the response of the instrument to change in the measured variable. And for the fidelity is the degree which an instrument indicate the change in the measured variable without dynamic error. Okay, so we finish on the performance characteristic, and now is the statistical analysis. The statistical analysis is the separate as far as possible the truth from the error, which is narrowing the define the region of doubt. Okay, this we use the statistical method, and the interpretation based on the large number of the measurement is usually required. For example, I think some of you, maybe you are already learned about the engineering mathematics on the statistic. Okay, here the simple statistic method. Okay, for example, the mean deviation, the average deviation, and also standard deviation is defined. Okay, where the arithmetic is the sum of set of n numbers, which is we can like a average lah. Okay, mean is average, and the deviation is the difference between the average and the test data. Okay, and for the average deviation is the absolute of the deviation over the n. Okay, the numbers set of number. And also the standard deviation is the degree. Okay, means the standard deviation has to be root square of the average deviation. Okay, here is the exercise. Okay, the table 2 show the data from the capacitor measurement, which is calculated. Okay, which is this mean average equal to xn equal to x1 plus x2 until the xn. If there is a question on this, which is from number 1 to number 10 is like this. So the average value of the xn is the total number of this over 10, then we can get the average. And also with the deviation on each part of this minus to the average, when we can get the d1. But for the deviation, don't forget, not only the d1, you have to find it d1, d2, d3, d4 until d10. Okay, this is only the equation. But for the if there is exercise or the question for the midterm or what, please find also for d1, d2, d3 until d10. Okay, because d1, d2, d3 until d10 can be used in the next formula, which is in the average deviation. You have to put inside it. Okay, which is the absolute value for the d1, absolute value for the d2. For example, okay, if you find the value of this 0.999, for example, if the value of 998 minus to 0.999, then we can get minus 0.001. Then if we want to find the average deviation, it will be absolute, and we can get a 0.001, not a minus 1. Okay, and also for the standard, this is easy, and you just times 2 is squared, and finally you have to root square. Don't forget, the standard deviation is n minus 1, not n minus 1. Don't forget it. Okay, so as the limiting error, the limiting error is the accuracy of the measuring instrument when it's guaranteed within a certain percentage with a full scale reading. For example, if you say that manufacturer will specify the instrument to be accurate at plus minus 2% for full deflection. Okay, suppose the accuracy of 0 to 100 voltage specified as 2% for full scale. So that means if the error is guaranteed 2 volt for any readings, if the voltmeter read 50 volt, okay, because of the accuracy is 0.100 is 2%. When the voltmeter is reading 50%, then we can say that, and the error is 2 volt. So that means 2 over 50% times 100, when we can get a 4% error. Okay, for the value for the what we call limiting error. Okay, but if 2 over 100, and we can get 2%. But now is 2 over 50 volt, then we can get 4%. Okay, because the value, the full scale is a 50, not 100. Okay. So for the limiting error is for the instrument is percent of the accuracy times the full scale. Okay. If the full scale is the 100, then we can get 2% times to 100. If 50, then 2 times 50 is a 4. Okay. Okay, so the limiting error is the measurement of percent, which is the magnitude of the limiting error over, for example, 2 volt over 50 times to 100, we can get 4%. Okay, this is same lah, limiting error. And for the limiting error example, for example, you see 600 volt. Okay. Kalau you all ada masalah ataupun tak faham terlalu laju, bagi tahu Okay. Because I just say about the solution and we can you can identify. Okay. If you are not understand or what, just put your hand up and ask me what you are not understand lah. Okay. So just please ask me. Don't worry. If not, I will just go through. Okay. So example 1.4 here, which is you have the voltmeter 600 volt. Okay, with the accuracy 2% for the full scale. Okay. So for example, if you are calculating, you now need to calculate the limiting error when the instrument is used to measure the voltage 250. Okay. So the full scale is changed to 250. Okay, change to 250. Even the voltmeter can go for 600 volt. Okay, so here the magnitude of the limiting error is for this one is 600 volt. Okay, and then you know that 600 volt, for 600 volt the limiting error will be 12 volt. But if you want to find a 250 volt, the limiting error percentage is already changed to 250. So 12 volt over 250 times 100, you can get 4.8%. Okay, because the full scale is changed to 250. Okay, but to find the limiting magnitude of the limiting error, you are given 600 volt. So you know that 2% to 600 is 12 volts. Okay. So if the ordinates or crate at deviation are equal to 0.6745 sigma, the half of the area under curve is enclosed, and this limit the quantity R is called as probable error. Okay, for the standard deviation, okay, for the standard deviation is sigma. Okay, then we can find it the Rm equal to R over n minus 1. Okay. Okay. How about the summation error? How to sum the error? When there is a two or more quantities, with each of it has a error. Okay, and how to combine it on that equation? Okay, the combination can be normally done by addition, subtraction, multiplication, and the division operating. Okay, where for example you have the device have the error like y plus minus dy or y plus minus dy over y form, we can assume that error caused by the two or more readings, by each of it has their own error and combine in a worst case. Okay. For example, if you want to summation the error, okay, for example, A plus B, A and B, both of the instrument has the error, which is both of instrument as like a sigma A and also sigma B. This is absolute error of the A and B, and percentage of the error, limiting error, is a percent A and percent B. Okay, so if you want to, the unit and the error for A and B can be written as A equal to A plus A sigma A, or in term of limiting error, we can put A plus percentage A. Okay, for example, 2% or what. And on the other hand, for the B also, and this error can be included as B plus sigma B and delta B, and also equal to B plus percentage B. Okay, either of it you can use it. Okay, it based on the question lah. What they use, is it delta or percent? Any mathematical operation that use A and B will produce a summation error. Okay, based on this two device, we can get the combination of the mathematical operation. For example, A plus B, we can get the delta C is equal to plus minus delta A plus delta B. For the mathematical operation for the A minus B, we can get the delta C is equal still plus minus delta A plus delta B. Meanwhile, for the C equal to A times B, okay, for the times, we can get the delta, the percent of the combination, the summation error is a plus minus percent A plus percent B, while for the division is a it is the same for the multiple, which is a percentage C equal to plus minus percent A plus percent B. Okay, this is how the summation error can be defined, can be done, okay, based on the mathematical operation like this. Okay, here, okay, we see that there is a given certain measurement, a limiting error for voltmeter at 70 volt. Okay, which is the percentage of A is 2.143, and for the ammeter is a 80 milliampere, which is the percentage of error is 2.813%. Now they want to determine the limiting error of the power. Okay, now is a determine the limiting error means summation. Okay, when it's come to summation is a, you can see a like this, which is the limiting error percentage can be a plus minus percent A plus percent B. Then we can just directly combine the error, which is 2.143% plus 2.813%, and we can get 4.956%. Therefore, from the power, we can find that voltage time to arus atau current, voltage time to current. Then we can get V V times to I. Okay, so V times to I, we can get the delta C. Okay, the percentage C. That percentage C is percent A plus percent B. So we know that we need to use a power as a like this. Okay, which is a percent C equal to plus minus percent A plus percent B. Okay, now we can go for next exercise. Okay, which is 150 volt. Okay, voltmeter and 100 milliampere. Okay, ammeter. Okay, here we are given, okay, measurement of the current is in the circuit, the DC source is series, okay, which is a resistor. Both of the instrument has the accuracy, okay, both has the accuracy 1%, okay, full scale. If the reading on the voltmeter is 80 volt, and the reading of the ammeter is 70 milliampere, what calculate the limiting error? Okay, calculate the limiting error. Okay, limiting error is the percent. Okay, percent A and B. Okay, so you know that there is a voltmeter and also the ammeter. Okay, now the same like previous calculation. Okay, for the voltmeter, for example, you know that the voltmeter is 150 volt. Okay, the ammeter is 100 milliampere. So if the accuracy is 1% for both, then you know that the limiting error for the instrument is 1% times 150 is 1.5 volt. For the ammeter is 1 milliampere. because 1% times to 100 milliampere equal 1 milliampere. Okay, for the limiting error measurement for the percentage, you need to find it 1.5 volt over 80. Okay, because the reading is already changed. The full scale is to 80 volt. Okay, for the ammeter is 70 milliampere. So 1.5 over 80. Okay, 80 is given, and 1 meter milliampere over 70 milliampere, and get times to 100, and you can get 1.429%, and this one is 1.875%. Okay, since the to combine the limiting error, you have to plus it. Okay, you have to plus it, and you can find 1.875 times 1.429, and you can get 3.3%. Okay, almost 3.3%. Okay, the better have the point per puluhan is better. Like 3.39 ke 3.34 ke, okay, is better than you put you kecil, you apa nama, you bundarkan, letak dua ke atas, is better. Okay, so the limiting error of the instrument is percent of accuracy times the full scale. Okay, and the limiting error is magnitude over measurement times to 100. Okay, this is for the this, and this is for this. Okay, this is the answer for all. Okay, the limiting error for the power is this. This is the answer, 3.3 something. Okay. Okay, so for the example 1.6 is the current of 2.0 at 0.01 ampere, which is this is flow to the resistor at 100 plus minus 0.2 ampere ohm. Okay, so you have a current and you have the resistor. Now you want to calculate the power of dissipated. Okay, power. Okay, you want to calculate the power dissipated and the limiting error. Okay, what is the what we call it, the formula for the power? P equal to VI. Okay, and V can be what we call it, separate into V equal to IR, and V you insert in the back, and you can get I times I times R. Okay, so you can get I squared R. Okay, since the value is 100, and you can get the P equal to I squared R is 400 watt. Okay, meanwhile at the same time for the voltage error, you can find it as a 0.01 ampere to 2 ampere. You can get the percentage, the limiting error. Meanwhile for R is 0.2 ohm, okay, over 100 ohm times to 100%, and you can get 0.2%. Okay, after you got this, because the IR, okay, you can find it as a percentage of the power. Limiting error for the power is percent I plus pi plus R, because it's the same like this lah. Okay, V times I, which is A plus B. Okay, so if you have three things, I times R, so that means I plus R. So that means 0.5 plus 0.5 plus 0.2. Then you get 1.2%. Okay, this is how you can get the limiting error for the power dissipation dissipated. Okay, for the limiting error, you can get by 1.2% itself to 100%. You can get 400, and you can get around 4.8. So the delta P is 4.8 watt. Okay, by using this value to the 100% for all the full scale, and for the full scale value is 400, and you can get 4.8 watt. Okay, this is how we can find the limiting error and the limiting error for the power dissipated and for using the percentage. And for the power dissipated also can be then you can calculate 400 watt times plus minus 1.2% when it comes to percentage. When it comes to absolute error is 400 plus minus 4.8 watt. Okay. Very long. Okay, I think I will stop our class until now. Boleh ke? I think part 3 I will go for next week.
Boleh sir.
Boleh sir.
Boleh Okay, good. Alright, I think until here there are some tutorial. For example, in tutorial tutorial 1. Okay, there is some question. Okay, there are some question that has been discussed. Okay, for the absolute error and for the statistical and the false measurement. I hope you can do this. Okay. Okay, I hope you can do this until which sorry. Calculate. Okay. Oh, okay. Okay, for the tutorial, okay, you can actually do all. Okay, if you can. Okay, because I think what we learned today, okay, can already covered for all the tutorial one. Okay, for your information, as I said, mentioned before, the tutorial I will take it as 5%. For you can see here, for tutorial 1 and tutorial 2 is 5%. For tutorial 3 and tutorial 4 is 5%. For tutorial 5 and tutorial 6 is 5%. So that means for the assignment, this will be an assignment for you. Okay, for the 5%, 5%, 5%, total is 15%. Okay, so I hope you can do your tutorial exactly, and you can send to the teams. Okay, but for now I not yet put the tutorial in this. I didn't put yet the tutorial, the assignment. Later I will put the assignment and you can put all the question, the answer inside there. Okay, is it okay?
Okay.
Okay, so I think no worries because this is also including the answers. Okay, and you can check by your own. Okay. All right, I think that's all for today. Is it okay? Okay lah. So I hope to see you by next week. Maybe next week I think I will do it on Friday because next week Tuesday is a holiday, and I will take Monday as my holiday also to go rentas negeri. Okay, so next week Monday we don't have class lah. Okay, for this class I will do it on Friday. Okay, is it okay for you all?
Okay, sir.
Okay, thank you very much for today. Okay, before we finish, I want to take attendance list. Okay, I will take attendance list. Okay, wait a minute.
Saya nak tanya.
Yes,
Yang
saya.
tutor ni kan, due date dia tu bila?
Tutorial.
Aha.
Okey, tutorial nanti dengan tutorial 2 sekali. So lambat lagi sebenarnya, tapi you boleh buat dulu.
Okay. Thank you, sir.
Okey sebab dia sekali 2. Sekejap 10. Okay, fine, good. Okay, that's all for today. Okay, thank you very much everyone. Okay, have a nice day. Assalamualaikum and goodbye.
Thank you, Doctor.
Okay, salam sir. Thank you, Doktor.
Thank you, Doctor. Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doktor.